So, let's start. Well, those from home hopefully could be able to retrieve to come up shortly. So we're talking about decays and scatterings. Just to answer a technical question that people ask me, if you find any trouble, normally I tell you exactly until what time you have to put the problem sets. If you need extension or something, you simply write to me. That's not a big deal. Don't get too nervous. If I don't answer right away, it's not because I don't like you, because I'm just too busy. That's all. Same goes for people who ask about my lecture notes. They are not ready. I keep on editing them, and they will be up when I have time to do that. So nothing against any of you. Simply I'm extremely busy, those who know. Now, okay, so we are basically talking about decays and scattering. We talk about lifetime particles. We talk about the Bright-Wigner formula for the lifetime of particles, right? And what? I know. I mean, we spoke about cross sections, and we started to speak about Fermi's golden rule. Thank you for that. And we spoke about golden rule for decays, right? So you had Fermi golden rule. אני לא יכול להתחבר לשידור. לא, זה בסדר, זה מחובר. פה רק לא מופיע, יש פה תמיד כזה נוסף של תלחץ וזה אוטומטית נפתח ונראה.
אני מזיז רגע טוב. אין פה סטודנטים לשבועות אחרי זה? לא? זה לא בכל הקורסים. לא בקורסים? זה רק זה חובה בקורסים. איזה כפייה יש שם? אבל זה צריך לשאול. אני מקווה שלא. אם כן עשיתי מעשר הרכז מהפעל. זה לא באמת משן הר של הרכז שכונה. הם טוענים שכן, לדעתי, לא ניסו לעבוד לדעתי, זה חניתי. יש לאנשים בבית הקישור הקבוע?
אני חושב שכן.
כן, כתוב בקבוצה שצריכים לשעה.
אתה יכול להקריא לי את הסוף שלו?
בסדר.
אני אקריא את זה כאן.
UQF מקף WMBX מקף TRO.
בסדר? אוקיי, תודה. אני לא יודע מה קרה שם. זה יופיע עכשיו חזרה בתור אייקון?
כן, אמרו לי.
לא
בתור אייקון. זה הבוקמרק, בפרום.
טוב, עזוב, אני באמת רוצה. תודה רבה. Okay, so good that this technical problem was solved. So we can now start again. So last time, again, we're talking about decays and scattering. We spoke about the Fermi golden rule for decays. Basically, a decay is when particle 1 goes into particle 2, 3, and particles. And then it's so it was a long derivation. We started with the basic decay rate formula, right? Gamma is S over 2 M1 integral M squared. M is the matrix element. 2 pi to the 4 delta to the 4 of P1 minus P2 minus Pn. Multiply pi from j equal to 2 to n, from 2 to n, 2 pi delta pj squared minus mj squared theta ej e j divided by 2 pi to the 4th power. Right. So this is the decay rate. This is a factor S that takes into consideration the possibility of equal outcome particles. Right, so it's 1 over n factorial. M is the matrix element. I'll show you today how we calculate it from Feynman diagrams, basically, essentially from Feynman rules. I will not give you, I'll not be able to give you the full. Unfortunately, I will not be able to show you completely how the derivative is going. I'll just show you the rules, because completely it's a perturbative approach which requires half a semester in quantum field theory, basically. Delta is the delta functions of the momenta, essentially representing conservation of momenta. Total, and then of each particle by itself. Theta is there to ensure that the energy is positive. Then we end up, it's a little bit technical, but we ended up when we get to 2 particles. So, a specific example of 2 particles decay, decay into 2 particles. We got 1 goes into 2 plus 3. So here j is equal to 3. So n is equal to 3 here. We ended up, after some mathematical manipulation, that gamma is equal to s p divided by 2 8 by m1 squared, the matrix element squared. P is the magnitude of the momentum of one of the outgoing particles. That was something that somebody asked me, I didn't give a proper answer. It doesn't matter which one, because we're working in the center of mass frame. So this is the momentum of, or magnitude of momentum of outgoing particle. And specifically, it can be shown that it will be equal to 1 over 2 m1, m1 to the 4 plus m2 to the 4 plus m3 to the 4 minus 2 m1 squared m2 squared minus 2 m1 squared m3 squared minus 2 m2 squared m3 squared, all that to the power 1. Another interesting thing that you might be noticing is that we actually never had to solve the integral because of all the delta functions. So we didn't really have to solve anything. Well, not the integral, right? And all these delta functions especially essentially represents the allowed phase space. How many outcomes are available. And the whole essence behind Fermi's golden rule, I actually just talked to Eli, who's going to teach that in quantum mechanics, and he says it's about 2-3 weeks that you'll get it. Not exactly in this form, because it's not using 4 momenta, but the idea should be the same. Is essentially that the particle can decay with equal probabilities to all the possible allowed outcomes. That's the physics behind it. Yeah.
זה לא פשוט הביטוי של הימים, אי אפשר לצמצם את זה, כאילו זה לא פשוט m1 בריבוע בין 2 בריבוע בין 3 פה, לא?
תבדוק ותראה. If it was, it would be.
נכון.
More questions? Okay. No? Now let's try to do it briefly as much as we can. So this is for decay, right? Now for scattering, the formalism is exactly the same. So it's just a bit, the integrals even look the same, they're slightly different. So instead of decay rate, in scattering we calculate the cross section. So for scattering, it's another one thing which kept some of you slightly confused, right? Scattering is where you have two particles, 1 plus 2 goes to 3 plus 4 plus n, right? And there is a key difference between decay and scattering, right? In decay, you can always go to the particle's rest frame, right? So in a certain frame, the particle is at rest. For a different observer, it may look like it's not at rest, but you can always go to the particle's rest frame, and then it just splits into two particles. In scattering, this is not the case. You can go to the rest frame of one particle, but in that frame, the other particle will have some momentum and energy, which is more than the restless energy. Right, so this is a key difference. Again, the scattering cross-section is calculated the same. I'm not going to give you the full how we got into this equation, again, because that is within the framework of quantum field theory. But the cross-section, I'm just going to give the outcome, sigma, which is S, it's the same as over 4, square root P1 dot P2 squared minus M1 M2 squared. If I don't put a vector, that always means it's a 4 vector, right? Just to make sure that you're with me. If I want to refer to a 3 vector, I will put a vector on top of it. If I don't put it, it's a 4 vector. And then the integral looks quite the same. M squared 2 pi to the 4 delta to the 4. Now we'll have P1 plus P2 minus all the other P's. P3 minus Pn. And then conservation of each momentum of a single particle by itself. J from 3 to n. 2 pi times delta Bj minus Mj, Bj squared minus Mj squared. Beta of Bj0, ensuring that the particles are real, they have a positive energy, and then d to the 4 Bj over 2 pi to the 4. So of course Pj is the form momentum of particle J with mass Mj. S is the same as what we have, a statistical factor to ensure we do not double count identical particles. Phase space is the same, so we can just proceed along the previous lines. I'm going over that briefly. It's technical, but modulo some mathematical typos which can easily be fixed. There's nothing too much to go through. If you get confused, just go over very slowly and make sure that everything is clear in your mind. So, performing the Pj0 integral, perform integration over Pj0. Now sigma, which is S over 4 square root P1 P2 squared minus M1 M2 squared integral M squared have 2 pi to the 4 delta to the 4 P1 plus P2 minus P3 minus Pn, and then pi j equal to 3 to n. Remember we had this 1 over 2 square root of Pj vector squared plus Mj squared, and then you're left with d cubed Pj over 2 pi cubed. of course, Pj0 is Pj squared plus Mj squared square root. And same Pj0 that occurs inside the delta function, and also we said inside the M is in general a function of the momentum. Right? Pj0 again, the energy. Yeah.
Don't we need the delta function in the okay.
I checked this equation this morning. I had a typo in my original maths. That's part of the reason why I don't post it. And to fix it.
שם בשורש זה וקטור מה הפיצ'ר?
Yeah. I did the integration over Pj0. It's no longer with us. And of course, this is too general. So if we really want to make progress, we need to be slightly more specific. And of course, we'll take the simple case. So example, which is two-party scattering. Scattering gives 1 plus 2 goes to 3 plus 4. 3 plus 4 can be the same initial particle, or they can be other particles. That's okay. So in the center of mass frame, what do we have? What do we know about the momenta of the two particles?
Equals the opposite of the second.
Exactly, right? P2 vector is minus P1 vector. And then I'm going to prove it to you. So you may get it homework or may not. P1 dot P2 squared minus M1 M2 squared is equal to E1 plus E2 multiplied by the magnitude of E1. I'll put here easy to show. Just because I can't write it. And then you decide for yourself whether it's easy or not. And then we have actually it is easy to show. And then you get that sigma is S over 64 pi squared. E1 plus E2 P1. Then the integral. As you've noticed, I removed all these pi's and 2 pi's from here. Get the 64 pi squared, so we're left with M squared delta to the 4 P1. Right? Now we have E1. Sorry. So delta to the 4. Sorry, I just jumped. Delta to the 4. P1 plus P2 minus P3 minus P4 divided by what we have here, square root of P3 vector squared plus M3 squared multiplied by square root of P4 squared plus M4 squared, and then d cube P3 d cube P4. Which already looks nicer than that one. Okay, this transition should be quite straightforward. And then, as we did before with the delta function, as we did before with the delta function, on the right, delta to the 4 P1 plus P2 minus P3 minus P4 is equal to delta
E1 plus E2 minus P30 minus P40 times delta cube of P3. P3 plus P4. So this is just conservation of energy and conservation of momentum, right, in the center of mass frame. And that we can use to carry the integral over P3, P4. So just the minus P3, Px. So P4, of course, is minus P3. Which ends up by writing sigma is equal S divided by 8 pi squared E1 plus E2 P1 integral M squared delta E1 plus E2 minus, well, P30 we can simply write down as square root of P3 vector squared plus M3 squared minus square root of P3 squared plus M4 squared divided by square root of P3 squared plus M3 squared square root P3 squared plus M4 squared d cube P3. Okay, is that clear to everybody what I did here? The solution should be quite straightforward. Just remember that P4 is minus P3. Yeah. P4 is equal minus P3. And just plugging what we have here, everything gets pretty straightened up. Now we have a slight problem. We said that M depends on P. But now I don't think it can be seen directly from this calculation. M also depends on the vector P, so also on the direction of P. So we cannot do the full integration without specifying how M depends on angular dependence of P. Again, P3, right? The momentum of one of the outgoing particles. Which if we know the momentum of the second outgoing particle because we're in the center of mass frame. So instead of making an attempt to fully solve it, fortunately we don't really need to do that because we can look at the cross-section per unit solid angle. Right, so for a given direction. So since now M squared depends on the direction of P3, as well as the magnitude. We do not carry full angular integration. Rather, we look at the cross section per unit solid angle. Rather look at cross section per solid angle, namely d sigma d omega. similar to what Rutherford was doing. Okay, cross section, how much we get per unit solid angle. That saves us the need to do the full calculation. And for that, we can do so basically we are essentially bypassing the problem of knowing the angular dependence of M. Or rather, we write down d cubed p3 is p squared p3 squared. P squared, let's just write it like that. dp d omega. So every d omega goes out to the sigma d omega, and we write down the sigma d omega is s over 8 pi squared E1 plus E2 E1. Then integral over the magnitude of the momentum from 0 to infinity of m squared delta we have here E1 plus E2 minus square root of P3. I would just P. Since we only have one P, I just omitting the subscript 3. But remember that this P is really P3. As minus square root of P squared plus M3 squared minus square root of P squared plus M4 squared dividing by square root of P squared plus M3 squared square root of P squared plus M4 squared P squared dP. So in fact we already had exactly this integral in the last lecture, right? Remember? I hope you do. So we already had this integral. None of you objected, assuming you're all unconscious at that point of the lecture. Then I'm simply going to repeat, and we end up that the sigma, the omega, is 1 over 8 pi squared. So remember, we just had M2, which is now replaced by M4, and M1 is replaced by E1 plus E2. Times S M squared divided by E1 plus E2 squared PF over PI. And if you want to add units, which is easier for calculation, correct units to add would be H bar C squared. Put it in a different color because now I'm switching units. So this is correct, right, in natural units. But if you want to adapt different units, it would be normal units. PF is the magnitude of the outgoing particle's momentum. It doesn't matter which one because we're in the center of mass frame. PI is the magnitude of the incoming particle's momentum. Again, it doesn't matter which one because we're in the center of mass frame. Right, PF. Magnitude of incoming, sorry, PF is final, outgoing. Those equal CM frame. PI is the same of the incoming.
questions wasn't that hard. So to bug me more.
יכול להסביר טיפה על זווית מרחבית רק או שזה...
אומגה, זווית מרחבית?
כן, כאילו, לא.
Did anybody see what is omega? Guys. Sphere. Theta, right? And phi. Right? So if you want to go here, you get the d theta. Right? If you want to go along this direction, you have d phi. Right? So if we're taking the sphere and divide it into small surface area of a sphere, right? We divide it into small pieces, right? Then the surface area, what's the size of the surface area?
Omega.
What? Right. 3r squared d theta d phi. This is r. Sin theta. Correct.
Okay.
Yeah. R squared d omega.
Oh.
זה גם חובה. Okay. Solid angle, right? Just 3D.
כאילו זווית של חרוט. הראש שלה, אם יש לי חרוט, אז הראש שלו, הזווית שיוצאת משם, זה פשוט זווית מרחבית, זווית
You mean you have something like that? Yes. That's a different angle. I mean, this is a 3D. That's a simple definition. I'm going to think of it in terms of this angle from here to think. So the standard definition.
Can you explain again what you do with... כאילו כתבת שם, since now m squared depends on the direction of p3, כתבת שם שהוא משפט, ואז כאילו אמרת we do not carry the angular integration.
Right. If you remember, yeah.
למה? כי אם אתה אומר שאתה כן תלוי בכיוון, אז למה זה לא תלוי בזווית המרחבית?
I don't know. Last time when we spoke about decay, right, really we have three integrals. It's dqp, right? What I should write is three integrals here, right? dpr, dp in the magnitude of p, and then theta and phi. Now, when we did last week, when we did the same calculation for the decay, right? I just said, okay, integral over the phi will give 2 pi, integral over the theta will give 2. So we just have the 4 pi and took it away. Right, 2 of the integrals, right? What I said now, I cannot do it because I can only do it if m is not depending on the angle. If m is independent on the angles, I can do the angle integration. But if m depends on the angle, then I cannot do the angle integration. That's all.
Okay.
Okay.
אז רגע, אמרת בסוף שכאילו, אז איך עשית לעשות את האינטגרל אם הם כן תלוי בזווית?
Well, that's why I'm not doing the integral. I'm just taking the cross-section per unit solid angle.
Okay.
Okay. So the integral is dqp is equal to p squared dp d omega, right? And the omega, the theta d phi, right? I just say, okay, I'm not going to do the integral. I just look at the sigma over the omega.
Okay, thank you.
You know? Okay. One last comment that I want to put is about the dimension of M. The dimension of M, the magnitude, again, I did not tell you too much about it, but the dimension of M depends on the number of particles involved. So, just a comment.
the dimension of M depends on the number of particles involved. Right. M is the matrix element essentially. So we count the external lines in the Feynman diagram. So the total number of incoming plus outgoing particles. We don't care about what happens in the middle. So if there are four n external lines, incoming plus outgoing, right? The dimension of L is the momentum to the power 4 minus n. So dimension of n, dimension of m is the momentum, which is just the mass to the power 4 minus n. So if we have a two-body scattering process, what's the dimension of m? If we have a two-body scattering process, what's the dimension of m? Unitless, right? Dimensionless. Okay, so for two particles going into two particles, we have m is dimensionless. Now m equal to 0. If we have a single particle decay into two particles, dimensionless. So what's it? If you have a decay of one particle into 2 plus 3,
Momentum.
what?
Momentum.
Yeah, we'll have a dimension of momentum. Etc. What?
If we have more than 4
Different dimension. Same problem. Perfectly fine.
How do we get to the values?
Oh, that's a good question. Now let's try. Oh, that's a good question because now I'm going to answer this question. Okay. Any questions about that? No. Okay. So now what we're going to speak about is Fermi's Feynman rules. So we spoke about Feynman diagrams, and I kind of mentioned it to you that these nicely looking diagrams are really a representation of some conceptually and mathematically very heavy things. Right? Feynman's ingenuity was that he managed to take some huge integrals that people did and knew before him and make a nice small cartoons which capture the whole physics with a simple set of rules which essentially make calculations extremely simple. But philosophically there are some very deep things inside of that these simple rules. So right now, I kind of talk a little bit about the philosophy behind it, but I will definitely give you the rules so that you know what they are. So Feynman rules. So Feynman rules are there to calculate the matrix element M. Okay, so this is what we want. The amplitude M. These rules are used to calculate the matrix element M. Now I know it's a bit confusing. I'm using the term matrix elements if you're really familiar with that. But again, when I'm thinking of a transition
of a one particle. I'm thinking of a particle, in terms of quantum mechanics. In a way, it's a state, in a big space, Hilbert space. It's not a Hilbert space, it's a Fock space, but you're familiar with Hilbert space. So I have a particle in one location in that space, and I'm asking, and something happens to that. So I have, think of a huge vector. The particle is somewhere here, and then time evolves, and I may find a particle somewhere here. Right? So I'm asking, okay, there is some matrix that gives me from transition from this state to this state. And that's why I call it a matrix element. Of course, if nothing happened, it stays here, and then the highest value would be on the diagonal. I care about not the diagonal. The diagonal is basically the uninteresting thing. Okay, that's a little bit about the philosophy of how I think of it. Now, the important thing is that Feynman rules, they depend on the model. So you're going to specify a specific model and get specific rules. What I'm going to show you now is a toy model which does not represent reality. Because I'm not going to include spins. And as I said, in reality we have fermions, which have spin half, and bosons, which have spin 1. So now I'm going to use spinless. So this is not reality in a sense, but it's a toy model that will give you the idea of how it works. So the Feynman rules depend on the model. So what I just said, you can deduce that there are different rules for fermions and different rules for vector bosons. For now, I don't care. I just look at so we're going to use a simplified model. We use a toy model. We will use a toy model. So in our toy model, we have only 3 particles. And so we call them A, B, and C. Toy model. In our model, we'll have 3 particles. We have only 3 particles, which we call A, B, and C. This is our whole world. And of course they have masses, so masses will be MA, MB, and MC. They do not have spin, so they're not real particles. Which means that every particle is its own antiparticle. And that also means we don't need arrows. And there is only one vertex which connects the particles of the 3 different types. Only one vertex is allowed that connects A, B, and C. Right, so the only allowed interaction, it looks like that. A, B, C. And the coupling constant of the vertex, we call it G. Now, we safely assume that particle A is the more massive one, so it's more massive than both B and C. So it can decay into B and C. So we said MA
is greater than mb plus mc. Of course, it's an assumption. You need to say. Is that A can decay into B plus.
אז בדעיכה ל-B ול-C להם גם מהירויות?
Right?
אז בדעיכה ל-B ול-C יהיו להם גם מהירות, או שזה גם פוטון?
Now, of course, the decay, I mean, this is the first order. I mean, now you can think, now let's see what you can do with this simple model, right? So this is the simple decay, vertex that describes the decay. A goes to B and C. But I have many more. I can have something like that. I can have A decays into a C and a B. And then I have an A and B and C. It's also a decay. It's a higher order corrections. Higher order decay terms.
But if G is much less than 1, then we can ignore it.
Yeah, I didn't say what is G, but yes. But I just want to show you, this is the lowest order possible decay within this toy model that we have. But I have a higher orders, like this is one example. I can have something
What
like
is
that.
the second day you write? What it present?
What? Excuse me?
The second day you wrote.
The second? Wait a second.
The right one.
A decays into B and C, but then they exchange a virtual A, and
Okay.
so they become
Okay.
C turns into a B, and then turns into a C. That's one option. We can have another option like A decays into B and C, which then merge together, forming an A, which then decays again into B and C. Yeah.
But like we said that the time in axis is from left to right.
Right.
And so A decays to B and C, and here like it's B and A merged to C. So I don't understand.
This is time.
Yes.
So at minus infinity you started with an A. At plus infinity you ended with a B and a C.
But
Everything else is virtual. Everything else is virtual. I do not see what happens here. That's an important feature of Feynman diagrams that needs to be.
How momentum is conserved?
Wait.
The mass,
Everything is conserved. Again.
the mass of A is bigger than C and B, so how can C exchange?
Again, guys. Let me do it. I think this is a tricky part. In a Feynman diagram, it's a computational tool. Okay, that's the correct way of thinking of it. It's a simple representation of some computations. Now, in reality, okay, we know what happens at t equal to minus infinity, which is here, right? T equal to minus infinity. We know what happens at t equal to plus infinity. Everything in between we don't know. Again, think of it in reality. We are doing an experiment, right? What is the experiment? For example, in CERN, right? We take two particles, we make them collide, and we end up with two particles, right? Even if you think of it in terms of classical, right? We have two, let's say, elastic scattering. We start with two particles, and they get closer and closer, and then they will be scattered in some directions. I said in classical physics, classical mechanics, guys, questions? Guys, back there. Questions to me. In classical physics, we speak about potential. We say, okay, the particle interacts with a potential. Okay? We have a gravitational potential, we have an electric potential, right? Or we have some sort of a billiard ball, right? Let's say here, normally we speak about electric potential that causes the particle to repel each other. I said it again, in the framework of quantum field theory, which particle physics rely on, we do not have that. There are no potentials. Particles can only interact by direct exchange of other particles. This is a computational tool.
it's extremely useful to explain two things that classical treatment cannot explain at all, which is formation of new particles in interactions, right? We have a formation of new particles in interaction, and what else did we say? And conservation of relativity. So nothing moves faster than the speed of light. Okay, we must have this. So this is a different way of thinking. So the way we think of it, if we're looking at the scattering process, is okay. How does this particle, being aware that there is another particle here, they are exchanging some virtual particles. Now these particles are virtual. We do not. There is no way to measure them. They are not real particles. It's a computational tool. But they have many of the properties of the real particles. They cannot exchange just some, magical particle which we don't know. They exchange particles which are the same particles as we know exist in nature, but they have some. We cannot measure all the properties, but we do assume that they have the same properties, such as the masses of the or the charges of the real world particles. Sorry, not the masses, because they're what's called off the mass shell. And the logic behind it is that these particles do not live long enough to be able to measure, and because of Heisenberg's uncertainty principle, since their lifetime is very short, their uncertainty in energy is so big that they can get any value essentially. Yes?
בחלקיקים וירטואליים הכל, כאילו, חוץ מהמסה, הכל אבל, כל הגדלים שלהם אותו דבר כמו חלקיקים רגילים.
Yes.
והם גם נשמרים כמו חלקיקים.
Yeah, they are conserved. So the way to think of Feynman diagrams is computational tool. We do not know everything that happens in the diagram. We only know what happens at minus infinity and at plus infinity. Everything in between is a computational tool. Okay? Actually, I hope you all will take quantum field theory one day. This visualization is going to be extremely helpful in understanding what happens there, because there they just give you all the integrals without showing that. Then you can easily get annoyed by all these formulas of how to orient times and how to do all these integrals, because there you actually have to do all these integrals of the delta functions, etc., for four-dimensional integrals. But forget about it. What I want to show you now, so if you get the picture of this diagram, it's very easy to understand what happens in that in the quantum field theory. Yes.
So the virtual particles do or do not need to obey the rules we made for our model?
No, it does not need to be. Well, no. We in our model we only have 3 particles, so I'm not inventing new particles. All the virtual particles will be one of these 3 particles.
No, I meant about the one vertex that's allowed A to B and C.
Yeah, I said that means that I can only allow in each vertex that there will be in this toy model, it will connect these 3 particles. You cannot have a vertex that connect A, and B, for example. This I don't allow. It's not part of the model.
I meant the time direction.
What about it?
It goes from A to B, like.
Essentially, yes. I'm talking about the decay, so yes. A decays into B and C. Yes. So here again, I will always start from the left with an A, like I do here, and I will end up in the right with a B and C.
You only look from the start to finish, not what in between?
Well, what in between is my computational tool. I need that to be able to do the calculation, to know what is the decay rate, decay probability, to know what is the cross-section, if there is a scattering. That I need to do. Okay, but it's a computational tool. Again, what do I measure at the end? What do I measure? No, first I measure the cross-section. If it's a scattering process, I measure the cross-section, right? Which essentially the cross-section, remember, tells me what is the probability of seeing this outcome. Right? I want to give a prediction. I mean, I'm doing an experiment, right? I want to know what is the probability, given an initial conditions, that I will end up getting that result and not that result. This is exactly what the cross-section is all about.
Or I do decay experiment, which I take a particle and I calculate what is the mean lifetime, or what is the opposite, the inverse of that is the decay rate, right, the gamma. And I want to calculate what is the probability that this particle will decay into dead particles within that time, which is exactly what gamma is. Okay, so I have a given of radioactive particles, whatever, right, polonium, right, and I want to know what is it going to decay into and how long it's going to take. And that's exactly what we're doing here. Right, so I want to do this calculation. And this is the tools how to do this calculation. Yes?
You said that we don't know the coupling constant, and so we can't ignore the higher order.
I do know what is the coupling constant, but here I just said it is G. I did not specify anything else about it.
So
G.
if it can be also 1, for example?
Yes. That's
So
what I
how
said.
do we know if it converge?
Right. That's what I said initially. For the weak force, for the electromagnetic force, it is much smaller than 1. So we have no problem doing perturbations. Okay, this is a perturbation theory. We do a calculation, which is good to a certain order. We want to get to higher orders. We can do that. We'll just need to use more diagrams, many more diagrams, and we'll get a correction. When we go to the strong force, the coupling constant is of the order of unity. So we cannot do perturbation theory, okay? Which is a problem when we want to calculate, to make realistic calculations of things involving processes that involve strong force. It requires a different machinery.
Can it diverge or?
It diverge all the time. Diverge all the time, and you need to there are very clever ways of how to deal with this divergence. Okay, again, but this goes into quantum field theory 2. Okay, yes.
G must be between 0 and 1.
That's what I said. I didn't even say that. I said G is a coupling constant. I did not say what the value of G is. You're right that if G is larger than 1, then the more processes you get, then it will get higher, so that we need to ignore it first. In that sense, yes. Right now, I just want to show, I'm just showing you a few examples of corrections. Yes, another question?
בצד ימין של הלוח כתוב לה שתי דיאגרמות, שתי סרטוטים.
Yeah, I want to hear more. But
הן מתארות את אותו דבר?
Yes, the two diagrams essentially represent the same process. We start with a particle A, t equal to minus infinity. We end up t equal to plus infinity at particles B and C.
הכוונה שלי האם זה מתאר כאילו גם את מה שקורה בין לבין?
Well, that's the thing. This is what we think. Within the framework of this model, within these rules that I put here, I'm putting what can happen in between. So the first order would be a simple decay, one vertex. But this is not the only option. We can have that option as well. This will have 3 vertices, right? 1, 2, 3. This will also have 3 vertices. I can have another one. A goes to B and C, and then B itself will decay into an A and C, which will then merge and get a B. Again, each vertex connects A, B, and C. So that is another option, right? Or I can have the same with the C. A, B, C, turn into A and B, which will again convert into C. This will give me another 3 vertices. 1, 2, and 3. Now, if I want to calculate all the, to calculate exactly the matrix element M, right, I will need to do to zeroth order. First order will have only this one, which has 1 vertex. Then we have these corrections. For G, which is smaller than 1, this will only be corrections. If G is close to 1, these corrections will dominate. Yes?
Could the C ever decay into an A if its mass is smaller?
No.
Wait, so what are we seeing here.
These are virtual particles.
These are virtuals.
These are virtual particles. So we do not measure them. The only thing you measure is the properties of A at the beginning of the process, namely t equal minus infinity, and the properties of B and C at the end of the process. So again, think of it in terms of the scattering that you're used to, right? Start with that. Here there is a box, you don't know what happens, and you're seeing that.
Saf,
Right?
the integral that you're not showing us in complex number or that stuff?
Yes.
Okay, now
Of course
it
it
makes
does.
more sense.
Yes. Yes.
אתה מדבר על קירוב מתורת הפרעות מסדר ראשון, מסדר שני, אתה אומר כאילו בהינתן שאחד עם A ומדדתי בסוף עם B ו-C, אז כמה דרכים עם ורטקס אחד, עם שתיים, סבבה.
Okay. Yes.
So if virtual particles can disobey many things, what should they obey?
Well, I told you, they obey everything except the mass. Yes.
עם מספר הדיאגרמות השונות, היו פה שני כאילו כמו שאתה רואה עם שני מהלכים. גדל מהר מדי מאשר ש-G, כאילו החלוקה שלי דורכת, זה גם לא כן.
Start understanding the problems here, right? It's actually a miracle that it actually works, but it does. Right? And how to handle this in physics, there are a lot of divergences here. Right? In fact, it's very rare. There are rare cases where it does not diverge. QED, which we're learning, is one of those cases where it does not diverge. So we don't have divergence, things work out fine. But mostly it does diverge. Then, thanks to Kenneth Wilson, who showed us how to handle these divergences. That's why you put them, basically take all the divergences, you put them into the mass and you forget about them and it works.
אבל יש משהו פיזיקלית להתבדרות? כאילו, רואים את זה? איכשהו?
That's a very, what catches one word or there is a very delicate boundary between physics and mathematics here. This is a mathematical calculation tool. Okay? At the end of the day, this calculation tool ends up to be giving us excellent, amazing tools in doing physical calculations. Especially of these two things, the decay rates and scattering processes, as well as the ability to predict the existence of other particles, which were predicted by these models. Okay? That means that we are doing something right. But I mentioned that at the beginning. We know that this is not the end of it. We know that there are things which we are not able to predict, such as the masses of the particles. We know that the theory is incomplete in some basic sense, and I did not speak a lot about that again because of the time constraints. I mentioned that when we go to higher energies, the coupling constants do change, and there is a reason to believe that when we go to high enough energy, all the coupling constants of all the forces obtain the same value. This is called the Planck scale, which is extremely high energy. And that's called the GUT. If you heard the name, it's called Grand Unifying Theory. Okay. Not in this course. Okay? We'll wait for that. You have to go through a longer process to get to even start to talk about it. Okay? I just mentioned it to you. You know that it exists. And if it interests you, right? Quantum field theory is what comes after you fully understand quantum mechanics. Then quantum field theory 2 deals with all these divergences. By the way, what you'll see in the way it's being written here, they'll show you find the path integrals, which are essentially the same thing as these ones. They're all built together. It's just a different approach, right? So I don't know how much they will show you these things, but it's essentially the same thing. Just remember that I'm telling you. Okay, so what I'm saying, all these is what happens within this box. Okay, we know the starting point. We know the outcome. We want to calculate why we get this outcome and not that outcome. And this is the way we do these calculations. This is, I'm opening a window into this box here. This is what we believe that there is inside it. Right? So that we believe it just works. Okay? Come up with a different model. Beat Feynman. Good luck. Okay, we said, so I just want to show you, right, within this simple model that we have here, only have 3 types of particles, even they're spinless, so each one is its own antiparticle. Only 1 vertex is allowed, only 1, not many. Masses, there is some hierarchy, A is the most massive one. Still, if you want to do the calculation of understanding how the A decays, right, A decays, so it's something else, we take an A, the particle A, we wait long enough, and suddenly we're saying B and C. Right? That's a decay process that we have here. And it turns out that there are many ways that this can happen. We'll see this way. Now, this theory, for example, now this is a decay, but this theory, for example, does allow scattering. Well, we can have a scattering in this theory. How do we have a scattering, for example? Scattering within this theory. Right. So for example, we can have a scattering as a process between 2 A's, A plus A goes into a B plus B. This is allowed. Of course, you have to exchange C, right? So you can have an A, and A, vertices, C, B, and B. Right? Everything is legal here within the framework of this theory, right? Again, time goes like that. Start with 2 A's, we end up with 2 B's. Then you have to exchange a C in between. Or we can have a scattering between an A and a B. Right? Or A plus B goes to A plus B. Right? So now we already have 2 options, right? So one option is to start with an A and a B. And then A switch into B by meeting C, and B and C switch into an A. That's one option. Or we can have, so this is with a T, right? We have an A and a B, into a C, and A and a B. So the S, of course, spaceline. Right? So scattering here is allowed. It's in the framework of this model. Again, this is a very simple model, but it turns out that it's it allows many things. Right. Again, you only see what happens here. Right? T equal to minus infinity, and what happens here, T equal to plus infinity. Everything else is a big box, which we want to decipher. Decipher, namely, give us some tools to calculate what is the probability of seeing this specific outcome. Okay. And for that, Feynman kindly gave us a set of rules which are associated with each of these diagrams and are relevant to each model separately. So the rules I'm going to tell you are good for this specific model, but they would not, if you try to use them in a real life where particles do have spins, then you get the wrong answer. And because for spin, particles with spin, you have to have slightly different rules, which we will discuss when we discuss more sophisticated models. Yes?
These particles also don't have a color charge and
Yes,
electromagnetic
so
charge.
color, yeah. These are
So if I had a spinless particle with a color charge, for example, it shouldn't obey this rule?
No.
Either?
no. These are the Feynman rules are specific for a set for a given model. So the Feynman rules that I'm giving now are specific for this specific model. Okay? Yes.
When your output is B plus B, do you need to distinguish between them? Is there a different specific option where the B that came out from that A turns out the
No.
other way? No.
No. I mean, B and C are different particles. But I do not know which B is B. I mean, if B is, the way I present it doesn't matter. If I put B up or down, it doesn't matter.
It's the same B particle.
So there is no another diagram where the lower A produces the higher B.
Actually, we can have that, but it's not going to make a difference, right? We can have
B plus B.
Yeah, actually here we can have basically A plus B. We can do like that because they're identical. A, B, C, A, B. We can do like that. So that would make. Okay, I'll show that. That will be the U. Let's do it on time. So the Feynman diagrams for this. Let's do it because we're starting to run short of time. So Feynman rules. So the Feynman rules go like that. So Feynman rules go like that. So before we give the rules, let's start with a notation. Actually, this is the first one, right? Notation. We label all the incoming and outgoing particles, so all the real particles, momenta with a P's. So all real particles, momenta are labeled with P's. So P1, P2, Pn. Each internal lines, so virtual particles, momenta, are labeled with Q's. All internal particles are labeled with Q's. So Q1, Qn. We'll make sure that we discriminate the real particles from the non-real particles. With each line, we do put an arrow to make sure that we keep track of what will be the positive direction. To each line, we add an arrow to keep track of the positive direction. What does it mean, positive direction? So, forward in time for external lines. And arbitrary for internal lines. That's the first rule. The second rule, for each vertex, we write a factor of minus ig. Minus ig. Every vertex we see. G is the coupling constant, which specifies the strength of the interaction. Get to that later. G coupling constant represents strengths of interaction. 3. For each propagator, internal line, for each internal line, write down factor, write a factor of I divided by Qj squared minus Mj squared. Remember that this is internal line, so this is a virtual particle.
means that they are off the mass shell, which means that Qj in general is not equal to Mj. Force is a conservation of form momentum in each vertex. Each vertex conserved, or form momentum is conserved. In each vertex, form momentum is conserved. So we do that by writing a delta function of the form 2 pi to the 4 delta to the 4 of k1 plus k2 plus k3, where k is the form momenta ki, I is equal to 1, 2, 3, is the form momenta of particles entering the vertex. That's why we put the arrows, right? If we say the arrow gets in, we know it's entering. Well, what if the arrow gets out, so the particle is outgoing? It's a minus. Okay? So, for outgoing particles, we put a minus. Of course, the delta function here is ensuring conservation of energy and momentum. And that's why it's a delta form. Now, 5 is integrate over internal momentum. All this is done. For each internal line, you write the factor of d4qj over 2 pi to the 4. And then integrate. Internal momentum. Then the 6th part is to cancel all the delta functions. Actually, one delta function. Cancel the delta function. So after doing this integral, we will end up with an expression. We get an expression that contains 2 pi to the 4 times delta to the 4. Sorry, delta not to the 4. Excuse me. P1 plus P2 plus minus Pn, which will essentially reflect all the conservation of energy and momentum that there are. Again, after we integrated over the internal momenta, what we are left with is just the external momentum, right? Which has to be conserved. So we'll get up a delta function there. Then we're going to cancel this delta function And simply, so we erase the factor, this factor, and then multiply by I. Somebody was wondering about whether there are imaginary integrations. Right? The result is M. Why are we doing that? The erasing of the delta function is because we're going to end up with delta function squared. Right? And we don't know how to do it, and we actually don't need to do it because we already have one delta function. Because the square of a delta function is not really defined. And the multiplication by I is for the phase. This will get clearer later down the line once we get the photons and polarization and things of that phase. But right now, yeah. And then the last part is to repeat all steps or all diagrams, or each diagram, and then sum all amplitudes. Very simple.
There are an infinite amount of possibilities, right?
Yes, they are. So what?
We converge?
Maybe. If you're lucky. Okay, so let's look at the examples, right? Example 1. Lifetime of A. Yes.
If we have an arrow in time in the particle and the particle is its own antiparticle, doesn't it break the symmetry because it's have
Here no, because
direction?
we're not producing antiparticles here. Right? In this model, we cannot produce antiparticles. All vertices will just have A, B, and C. Right? Again, in more sophisticated models, it gets more complicated. But these basic rules give you a very good starting point. What? Okay. No, I will have to give the examples. So, lifetime of A, right? So the zeroth order, or the first order, right, is this one first. A, B, C. There are no internal lines. So we put momenta, P1, P2, and P3. One vertex. So we have one vertex. So from rule number 2, so rule number 1 we just did. Rule number 2 would give us a minus IG factor. No internal lines. Rule number 3 we don't need. Rule number 4, we have a conservation, so we have 2 pi to the 4 delta to the 4. We have 1 incoming and 2 outgoing, so it will be P1 minus P2 minus P3. That's rule number 2, right? This is rule number 4. We don't have internal momenta. So rule number 6 means that we don't have to, we take that, we cancel that, right? And we replace it by an I. So I have an I times minus IG, which is just G. Ta-da! We finished. So we got M is equal to G.
what is the point of rule 4?
Right. Rule 4. Wait, this was the simple example. Just a second. So if we go back to what we did, we end up at the lifetime, or the inverse lifetime. Gamma A is G squared. Okay. Is the amplitude of the outgoing, the magnitude of the momentum of the outgoing particle. G squared P divided by 8 pi ma squared. P, just a reminder here, P 1 over 2 ma, and have ma to the 4 plus mb to the 4 plus mc to the 4 minus 2 ma squared times mb squared minus 2 ma squared mc squared minus 2 mb squared mc squared.
We assume for that spherical symmetry. Does it apply?
Yeah,
No,
in decay, yes.
How it look like in the Feynman diagram?
Nothing. This is the final diagram.
Yeah, but
No,
what
that's
is presenting the spherical?
Well, okay. Maybe you're jumping. So one step. Is that clear? Or a question?
You told us that the dimensions of m
Yeah.
is m mass to the 4 minus n, and here
Correct.
n is 3, so
Yeah.
the dimension is supposed to be mass.
Yeah.
But in the gamma,
G.
In the gamma of A, the dimension of G is 1.
No, we have the same.
But it's energy divided by the energy squared, so it's 1 over energy.
No. Okay, you check it out. No, there should not be an issue.
Oh yeah, it's okay.
Yeah, it's fine. Yes.
אם אתה רוצה לקחת תורת פרופ, סדר שלי, שאתה פשוט כאילו סוחב מבחן באינטגרלי.
Okay, let's do, because we're running out of time, let's do another example. This was a simple example. Let's go to the second example, which is scattering. So example 2, scattering. A plus A goes to B plus B. Right? So again, have A, so P1, P2, then they will go at the end, it will go like that. P3, P4, some angle theta. To answer the question about the angular dependence. So, the lowest order contribution with a T channel that goes like that. A, B, A, B, so we'll have to be a C. So we're going to put an arrow, so P1, P2, so this is P3, this is P4, and I said in the intermediate one is arbitrary, so we can put whatever I want. So I can put it like that and call it Q. So now we have two vertices and one internal line. Right, we have two vertices, 1, 2, and we have a one internal line. So we have minus IG squared on the two vertices. We have one internal line, which will give us I over Q squared minus MC squared. And we have two delta functions. Each vertex with four momentum is conserved, and we have these two delta functions. So we have 2 pi to the 4 delta to the 4. What do we have? Here we have P1 minus P3 minus Q. That's that idea. And here we have P2 P2 plus Q minus P4. Yeah? Just following exactly the lines there. So overall, we have over here a minus, right? So let's see. And then we have an integrate.
Five.
Yeah, 5, right? So we have integrate over internal momentum. So overall, we get a minus I. Apologies for that. 2 pi to the 4 g squared integral 1 over q squared minus mc squared delta to the 4 p1 minus p3 minus q times delta to the 4 p2 plus q minus p4. Right? 4 we have this extra factor. You have a d for q. Now the second
it's supposed to be complex.
What?
Yeah, the answer to the integral is supposed to be complex?
No, wait.
Okay.
Now the second delta function here means that q is equal to p2 plus p4. So when we carry out that, we have that minus I g squared 1 over p4 minus p2. p4 minus, q is equal p4 minus p2. That's from here. Speeding up so I make mistakes. Squared minus mc squared. 2 pi to the 4 delta to the 4 p1. Q is p4 minus p2, so we have plus p2 minus p3 minus p4.
Does it really matter because you anyway cancel it?
Exactly. Now, as I said, once we get into number 6, we're left with one delta function, which we cancel and replace with an I. So all that is cancelled and replaced with an I. So overall, we have m is equal to g squared divided by p4 minus p2 squared minus mc squared. Quite cool. If you go back to what we saw a few weeks ago, right, this is the Mandelstam T variable. Explains why it's called a T channel when you do it like that. Now, of course, this is not the end of it because we have the what was related to your question, right? We can twist the B lines basically. We can go with different P's. So the twist will be that this P will get the P4 and this can get the P3. So one way to think of it. Right. B, but the important, these are identical, but the difference is in the momentum, of course. So this is the P1, this is the P2, now this will be the P3, and this is the P4. This is the Q. But essentially it's the same thing, just switching P4 and P3. So see, same as previous, but with P3 and P4 interchange. So we don't need to do anything, we just need to add that. So adding 1 gets m is equal to g squared divided by p4 minus p2 squared minus mc squared plus g squared divided by p3 minus p2 squared minus mc squared. Just to keep the symmetry. Just a second. Right, and this is a Lorentz invariant. Let me finish and then I'll answer questions. Just for the sake of completeness, so assume for the sake of completeness that MA and MB have the same masses. So MA equal MB equal M, and MC is massless. Then we have from here P4 minus P2 squared minus MC squared is just P4 squared plus P2 squared minus 2P2 dot P4, which is just minus 2P squared minus cosine theta. That is the same angle as I had before. And the same P3 minus P2 squared minus MC squared, which is 0. It's equal the same, but with 3 instead of 4, so it's equal to minus 2p squared 1 plus cosine theta. And then that gives that m is equal to minus g squared divided by p squared sine squared theta. And plugging it into the equation that we derived earlier, we have that d sigma d omega is 1/2, which comes from the identity of the two particles, and then g squared divided by 16 pi e p squared sine squared theta squared. What did we get? The angular dependence. Same as Rutherford scattering. Right, remember the two incoming particles and then the outgoing P1, P2, P3, P4, angle theta. Right? So we ended up, I did not still specify what G is, but we end up with the same angular dependence as Rutherford got. Should not be that surprising, but after a little bit of digestive time, we'll see where everything makes sense here. Yeah, I said it and I'll say it again. These Feynman rules that I put here are correct only for this simple model, toy model. In general, don't try to apply them to the standard model, because then you'll have to modify them because of the existence of various things such as speed. Okay? But I'm not going to surprise you that these are based on what we have here, so this is a good basis. Right, questions? There were first, yes?
Don't we need to sum over the possibility that C goes the other direction?
What do you mean C? What do you mean C?
The particle C.
What?
The particle C, Q.
You could be negative. What do you mean?
Yeah. Don't we need to sum this over?
Because you do not discriminate between these two particles. You don't need to.
And who is P and E? And in the end, who are P and E in the end?
This is the energy and the momentum of the outgoing particles. Okay. It's the same thing that we had. I just wrote it down, right? It's P3 or P4, which will be the same because we're working in the center of mass. So it doesn't matter which one. So just select, you work in the center of mass, select one of your favorite, These are identical particles, so they have the same energy, same momentum. Right, more questions? No. Okay, I hope I will have time to post the next problem set today. I'm just have a crazy day, as you might have already noticed. And if I can, I'll do it today. If not, I'll do it tomorrow. And of course, you get an extra day to finish it. Any further questions? If not, then I'll see you on Thursday. And also try to finish with that modification which I'm doing, so I can post that on as well. All right, so have a nice rest of the day. It's not raining, it was supposed to be. Thank you.
Yes, I can diagram that. Find out which one is the